Alright, so today we're working on section 1.4. We're going to be doing a lot of factoring today with special cases. This is factoring special form polynomials. So anytime that we factor, if it tells us to factor, to simplify, to get in lowest terms, all that stuff, the number one thing we do every time first is we look for a greatest common factor. In order to do that, we need to be able to recognize how many terms are in the problem. So like on number 2 on page 28, 4x minus 32. How many terms are there? Well, terms are separated by a plus or a minus sign. So I have the term 4x and I have the term 32, and that's being subtracted from the first term. So that's a two-term polynomial. The reason that's important is because for me to pull out a greatest common factor, every single term has to have that greatest common factor within it. So what does 4x minus 32 have in common? I'm going to look at the numbers first. The coefficient on the first term is 4. Does 4 have anything in common with 32? So does 4 have anything in common with 32? Yes. I can pull a 4 out. Then I'm going to look at my variables. I've got an x in the first term, and I do not have one in the second, so I cannot pull out a variable. That immediately tells me that I'm going to be doing my parentheses. Basically, to determine what's going to be inside the parentheses, all I have to do is I'm going to have two terms in it. I have to be able to multiply it back out and get to what I started with. So I have to have two terms. The first one, I'm going to say, what do I have to multiply 4 by to get 4x? I just have to multiply it by x. The second one is, what do I have to multiply 4 by to get negative 32? I have to subtract it by negative 8. I'm done. I factored out the GCF. So my GCF was 4, and I pulled it out. All right. So let's look at number 10. Same concept, but this one looks a little bit different. I can pretty much guarantee you're going to see some of these types on your tests. I just don't want it to throw you off just because it looks different. So I've got number 10 has two terms. One of them is 3v times the quantity of w minus 12. The other one is 7z times the quantity of w minus 12. All right. Now, let's see. Each term has 4 factors. I'm about to find out what they have in common. So my GCF, my greatest common factor, my first factor is a 1. My second factor is a v. My third factor is the quantity of w minus 12. In the second one, the second term, I have a factor of a 7, a z, and a quantity of w minus 12. So now I need to look and see which factors do they have in common. Does 3 and 7 have anything in common? No, I can't do anything. Does V or Z have anything in common? No. The last factor, w minus 12, they both have. So that is a factor that I can pull out. I'm going to pull out w minus 12. Over here I'm going to write my GCF is w minus 12. All right. So now, what do I have to multiply w minus 12 by to get back to 3v times w minus 12? Well, I'm missing the 3v, right? I'm missing this part right here. All right. What do I have to multiply w12 by to get back to 7z? I'm missing this part, so I'm going to have plus 7z. So basically everything that was left outside. Now if I wanted to double check it, I would multiply this w minus 12 times everything inside the second one. All right? So the first step, 100% of the time, is we need to pull out the greatest common factors. Okay, now we have a couple that we're going to refer to as potential perfect square trinomial. So what does it mean to be a trinomial? That means that it's a polynomial with exactly 3 terms. And I'm going to test to see if these are perfect square trinomials. The way I'm going to do it first is I'm going to recognize that the first term, so my first term is x squared, and my last term is 25. I'm going to check both of those. Are those perfect squares? Well, the square root of x squared equals x, so that is a perfect square. The square root of 25 is equal to 5, so that is a perfect square. Now, if I can take those two things, if I can take the square root of my first term and the square root of my second term and multiply them times 2, which would look like 2 times 5x equals 10x, if that equals my middle term, then that means that this is a perfect square trinomial. The benefit of that is if it's a perfect square trinomial, I can just write it as it's going to be a quantity squared, and it's going to be the square root of the first one, and it's going to be plus the square root of the second one in this case. Okay? The next one looks a little bit more difficult, but we'll handle it the same way. My first term is 16x squared. I already know 16 is a perfect square because it's 4 times 4. X squared is obviously a perfect square because it's squared. 121 is a perfect square because it's 11 times 11. So technically I could rewrite this thing as 4x squared minus 88x plus 11 squared. All right, we don't have to do that if we recognize it. I just want you to see how this works. So I'm going to take the first one, 4x, and I'm going to multiply it times the last one. And I'm going to multiply that times 2. 2 times 4x is 8x. 8 times 11 is 88x. So the fact that it is the same as the middle tells me it's a perfect square trinomial. So I immediately know it's going to be, and it's going to be 4x. It's going to be 11, and it's going to be minus in this case because my middle term is negative. All right, so that gave us one of each example, one a little more difficult than the other. But really, if I look at it and I see that this is 4x and 11, those are perfect squares, I can do that math pretty quick. So we should be able to get these answers without having to do a whole lot of trial and error. All right. Okay, the next special factoring case we have is the difference of perfect squares of perfect squares. All right, so some ways we can identify that pretty quick is we know the difference means subtraction. So if it's not being subtracted, it's not going to work. If it's of perfect squares, that means there's 2 terms. So on number 32, 9x squared minus 121, we've got 1 term, 2 terms, and they're being subtracted. Okay, so that's the potential to be a difference of perfect squares. If each term is a perfect square, then we will be able to do it this way. Okay, so what I mean by that is we could rewrite this as 3x squared minus 11 squared, right? That's the square root of 9x squared is 3x. If we can do that, then we're going to have our solution will always be the square root of the first one is the first term. The square root of the second one is the second term. One will be plus, one will be minus. Okay? What we need to recognize is that those are conjugates of each other. All that means is they are identical except for the sign between them is different. Okay? Difference of perfect squares. So let's look at number 36. Is it going to qualify? Well, it's binomial. A little different. This one's to the fourth power. Right? Let me make sure I wrote it down right. Yeah. So we've got one term, two terms being subtracted. The first one, if I take the square root of it, I get 8c squared squared. So that looks a little bit different there. Minus 9r squared. So do you see that? If I take the square root of 81, I get 9. If I take the square root of r squared, I get r. So I know that I can do it as conjugates of each other. So I'm going to have something times something. The sign in the middle is going to be opposite of each other. It's going to be the square root of the first one, so 8c squared. And then the square root of the second one, which is 9r. Alright, so that's how we factor the difference of perfect squares. I just want to make sure that we note, let's just say we do, I don't know, I wrote a number down, I'm making this up. Let's say we have something like x squared plus 4. That's two terms. Each one of them is a perfect square. Can we factor it the same way? Can we say that that is x plus 2, x minus 2? Well, if we FOIL it, x times x is x squared. X times negative 2 is minus 2x. 2 times x is plus 2x. 2 times negative 2 is minus 4. When I combine those like terms, they cancel out. I get x squared minus 4. So that's not what we started with. So that can't be the correct way to do it. All right, so what if we tried to do x plus 2, x plus 2? Do we think that would work since we have a positive? Well, let's see. When I FOIL it, I get that x times x is x squared. X times 2 is plus 2x. 2 times x is plus 2x. And 2 times 2 is plus 4. Combine like terms here, I get x squared plus 4x plus 4. So that one doesn't work either because I didn't come back to one I started with, which means that this one, the answer is it is prime. There's nothing I can do to factor it. All right? Okay, so these next ones, they don't fall under any of the things that we've done. We can't, on number 44, x cubed minus 8. I can't pull out a greatest common factor. They've got nothing in common. It's not the difference of perfect squares because x cubed is not a perfect square. 8 is not a perfect square. So I don't have those tricks that I can use. What we're going to talk about, though, is the sum and difference of odd powers. Okay, so when we talk about powers, we're talking about exponents. If we can find a way to write, these are binomials, each one has two terms. If we can find a way to write each term as to have the same power and that power is odd, then we have tricks. Okay, so on x cubed, that's already a perfect cube, right? 8 can be rewritten as 2 cubed. All right, so once you probably, to be good at these, you really kind of need to know that 1 cubed is equal to 1. 2 cubed is equal to 8. 3 cubed is equal to 27. 4 cubed, 64. 5 cubed, 125. All right, so and you probably want to take that all the way up to like probably to 10 or so. And then just be aware of it. Use your calculator to determine anything bigger than that. All right, so if I can write this as x cubed minus 2 cubed, then I have the difference of perfect cubes. There's going to be a formula that we can use. If it's the difference of perfect cubes, so if we have something like x cubed minus y cubed, the way that would factor is it's going to be x minus y, and it's going to be x squared plus xy plus y squared. All right, so basically it's going to be the base of the first one minus the base of the second one times the quantity of the base of the first one squared plus the base of the first one times the base of the second plus the base of the second squared. So on ours, what are my bases? My base on this one is x and 2. That's the bases I'm working with. So when I go to solve this one, I'm going to have the base of the first one minus the base of the second times the quantity of the base of the first one squared plus the base of the first one times the second. So I'm going to write it as 2x plus the base of the second one squared. 2 squared is 4. And I'm done. I didn't have to do a whole lot of math. I just have to recognize that 8 is the same thing as 2 cubed. Okay? So on this next one, on number 50, we have 216r cubed plus 64v cubed. The hint that tells me this is quite possibly going to be the sum or difference of odd powers is that my exponent on my variable is already cubed, and there's not a trick for me to get it less. If both of these had an r that I could pull a GCF of r out, then that would make it quadratic or to the second power. But because it doesn't, my first thought process is, can I rewrite this as a sum or difference of odd powers? On this one, obviously, it would be the sum. If it works out, it's going to be the sum because we have an addition sign here. So 216, is that a perfect cube? Well, let's see. 6 cubed is in fact equal to 216 because 6 squared is 36. Multiply that times 6 again, and you're going to get 216. All right. So I can rewrite the first one as 6r cubed. Make sure you use your parentheses here. If you don't, then the base is only r and you've changed the whole thing. It's that once you're cubing, both of them have to be in parentheses. Plus, well, 64, now you got to be careful here. I think our first instinct is to say it's 8 because we're used to working with the differences of perfect squares. But 8 cubed is actually 512. We've got to be careful there. 4 cubed is 64. All right, we see it right over here. 4 cubed is 64. Be careful not to mistakenly put an 8 there. So this one I would write as 4v quantity cubed. So now I have the sum of odd powers, so the sum of perfect cubes. The only difference here is it's going to look very similar to the difference, but I'm going to have, do it in green again so we match it up. If I have x cubed plus y cubed, so anything cubed plus something cubed, the way it's going to factor is I'm going to have x plus y. Notice the other one was x minus y. So those signs changed. And then the first sign will change. I'm going to have the base of the first one squared minus the base of the first one times the base of the second plus the base of the second one squared. So it looks really similar. The key differences are going to be, we've got those two signs are reversed. Okay? So on mine, I'm going to have the base of the first, which is 6r, plus the base of the second, which is 4v. I'm going to be multiplying that or times the quantity of the base of the first one squared. So 6r squared is going to be 36r squared. My sign here is going to become a minus, and I'm going to have the base of the first one times the base of the second one. So 6r times 4v. 6 times 4 is 24. R times v is just r times v. My last sign is a plus, and I'm going to have the base of the second one squared. 4v to the second power is going to be 4 times 4 is 16v squared. All right. So they're not just insanely difficult. The hardest actual math we did was probably identifying that 216 is the same thing as 6 to the third power. Everything else was memorizing the formula and plugging it in. All right. So now when I come back, we're going to work on one that has a higher degree that is still the sum or difference of odd powers. Okay, so now this one doesn't look too terrible just looking at it. We see 128 m to the 7th minus v to the 7th, right? So if we just casually look at it, that doesn't seem terrible. The tricky part, though, is the formula on this one is what throws most people off, but I'm going to try to break it down for you a little bit to make sense of it. Okay, so what my goal here is I see that the m and the v are to the 7th power. So those powers are the same. So that tells me that I can try and see if this works. The only way it's going to work is if 128, if I can rewrite it as something to the 7th power. All right, because I know exponents make numbers grow very quickly. It's going to be a pretty small number that I can multiply by itself 7 times and get to 128. Obviously, it's not 1, so my first step is going to go to 2. 2 to the 7th power is indeed 128. So I know that I can rewrite this as 2m to the 7th minus v to the 7th. So now I've done my trick where I've got them, both terms are to the same odd power. Okay? So now we're going to look at the formula, and I'll just give you a heads up, it ain't pretty. All right, so anytime that I have an x to the nth power plus or minus a y to the nth power, okay? So it doesn't matter what power it is if it's odd. What matters is both terms, it's the same. If it's 5, then if x is to the 5th, y has to be the 5th. If x is to the 9th, y has to be to the 9th. So as long as they're odd and they're the same, then I can use this formula. Doesn't matter if it's plus or minus. All right, so it's going to be the base of the first one plus or minus the base of the second one. It's going to be multiplied by the base of the first one raised to the n minus 1. All right, all that means is if it's to the 7th, 7 minus 1 is 6, it's going to be to the 6th power. All right, don't let that weird notation throw you off. Minus or plus x to the n minus 2. So now it's going to be, if it was to the 7th, it's going to be to the 5th. And I'm going to bring the base of the second one. So it's times the base of the second one. Plus x to the n minus 3 y squared. So you'll notice that on x, my exponent is decreasing by 1 each time. On y, my exponent is increasing each time. All right? And that's going to be plus or minus, and I'm going to keep that pattern going until my x gets all the way down to the first power. So what that would look like is when I do x to the 1, my y will then be to the n minus 2. And as you do this, you'll see that it's just working its way down because the exponents are the same when we started. As one decreases, the other one increases, and it does it at the same rate. So this will work out perfect every time. And my last my last term will be just y to whatever it started as minus 1. So just like my first term was x to the n minus 1, or the base of my first one to the n minus 1, my last term will be the base of the second one to the n minus 1. Everything else will just gradually decrease on the first one, increase on the second one. Okay? So, on the one we're working on, what that would look like is my base is 2m minus my base is v. Okay? Okay, so the way that it's going to start is I know that I'm going to have the first term, the base of the first term, and the base of the second here. I just got to decide, because my formula says plus or minus, I got to decide which one. I'm going to match what was in the original problem. That's going to be a minus. Now, if I start off with a minus, the rest of it, they're all going to be pluses. If I had started with a plus, then they would alternate. So, on the second one, it's just like up there. I have x to the n minus 1. I'm going to have 2m to the n minus 1. So this is going to be written a little bit different just so we have that extra step. It's 2m, n minus 1 is to the 6th, right? Plus, every one of them is going to be a plus. Now I'm going to have 2m to the n minus 2, which is 5, v. So because I'm multiplying it times the first one. I'm going to have plus 2m to the n minus 3, which is 4, times v squared, plus 2m to the third, v to the third. Notice those exponents are the same. That means I'm on the right track. And I'm going to start going the other way. In other words, now that they've met, it's going to be 2m to the second, v to the fourth, plus 2m to the first, v to the fifth. You'll notice that in our formula it says to the n minus 2. Well, 7 minus 2 is 5. Plus 2m to the 0 power, which is 1. And then it's going to be v to the n minus 1, which is 6. All right. Now I need to simplify it a little bit. I need to make it look a little bit prettier. You'll probably want to use your calculator on these whenever you start getting up into these big numbers. So my final answer is going to be 2m minus v. Nothing I can do in there. 2 to the 6th power is 64, and then m to the 6th. Plus 2 to the 5th power is 32, plus 2 to the 4th power is 16. Oop, I forgot my v over here. Easy to mess up on these if you don't take your time. 32mv plus 16m to the 4th. See, I almost did it again. It's m to the 5th there. 16m to the 4th v squared plus 8m to the 3rd v to the 3rd plus 4, because 2 squared is 4, m squared v to the 4th plus 2m v to the 5th plus v to the 6th. Okay, so there are definitely a lot of opportunities for us to make mistakes. We have to make sure that we're applying that exponent. So on the first term, I've got to make sure I apply that exponent to the 2 and to the m. And I almost messed up twice on this term right here. I need to apply that exponent to the 2, and I need it to apply it to the m. But at the same time, I cannot forget that I'm multiplying whatever that result is times v. So you saw me almost make the mistake. There wasn't a whole lot of terribly hard math in this problem, but there's a lot of steps, and we just got to make sure. Now, when I go to double check, what I'm going to look at is, do my exponents decrease on the first term and increase on the second as we go? So I've got to the 6th, to the 5th, to the 4th, to the 3rd, to the 2nd, and to the 1st. There's an understood 1 there, right? On the other one, I have, we'll just circle those. I have to the 1st, understood 1, to the 2nd, to the 3rd, to the 4th, to the 5th, to the 6th. All right. That your answer should look something like that. The only difference, if this had been plus v, m to the 7th plus v to the 7th, we can do this pretty quick because we've already done the hard work. Everything's going to be exactly the same. I'm going to have 2m. I'm going to have v. I'm going to have 64m to the 6th. I'm going to have 32m to the 5th v. I'm going to have 16m to the 4th v squared. I'm going to have 8m cubed v cubed. 4m squared v to the 4th. 2m v to the 5th, and v to the 6th. I know I'm going to have all that stuff exactly the same. The only difference is going to be the sign. So I started off with a plus, so I'm still going to start with a plus. But then I'm going to alternate. I'm going to go opposite, same, opposite, same, opposite, same. Okay, so if it's a sum of odd powers, we know it's a sum because of this guy, then my signs are going to alternate. Other than that, everything is identical. Okay, so that's going to get us through 1.4. I wanted to do an extra video on it because I know that there's a lot going on there and a couple of you missed class, so I want to make sure you are able to get caught up on it.